Okay, watch this. 9 out of 10 students get network topologies wrong in exactly this way, and it quietly costs them the grade. When you see computers placed in a straight physical row connected to a central hub, your brain immediately wants to scream bus topology, but that is the ultimate exam trap. Just because the physical layout looks like a line, the operational logic, how the data actually travels, makes this a star topology. A true bus topology absolutely requires a single shared common communication link or a backbone that every single device connects into directly. The visual arrangement of the hardware, it doesn't dictate the operational logic. So keep that in mind before you make this exact mistake on your real exam.
Right, let's dive into this. Welcome to this high-yield explainer. Today, we're going to master not just the core concepts of the Cambridge IGCSE computer science syllabus, but the exact exam secrets that will secure you full marks. We're taking all those dry, theoretical computing concepts and turning them into a clear, highly visual roadmap so that this information actually sticks.
So let's start with a foundational question. Before we can even touch complex algorithms, network data streams, or embedded microcontrollers, we have to understand the environment where it all begins. What actually turns high-level, human-readable programming logic into the executable, machine-level binary that a computer can understand?
The answer is an IDE. And the crucial point here is getting this definition exactly right for the examiner. An integrated development environment is software that helps programmers design, create, and test program code. In our case, we're looking at Visual Studio Community 2019. It gives the programmer this incredible suite of tools to write algorithms, autocomplete syntax, and instantly debug errors, all within a single, unified workspace. Basically, it's your command center.
Now, inside that IDE environment, you generally have two different ways to build your program. First up is the console application. This is a purely textual command line interface. It's beautifully uncluttered, totally straightforward, and honestly absolutely perfect for learning raw computational logic. On the flip side is the Windows Forms application, which gives you a graphical user interface, or a GUI. This is exactly what you'd use to program interactive, commercial-style applications. Think buttons, drop-downs, windows, the whole shebang. Now, while the exam primarily tests your underlying logic, understanding this structural difference really grounds your coding skills in reality. Okay, let's shift gears for a second from the software environment over to the physical world, specifically the topics you're going to encounter in Paper 1. We use these coding environments to solve real, everyday digital problems. Think about the smart thermostats controlling the temperature in your house, building up to complex banking security systems protecting global financial data, all the way to high-speed robotics on a modern manufacturing line. Every single one of these requires incredibly precise hardware and network solutions to actually function.
To truly master these physical embedded systems, we need to follow what we call the three-layer learning cycle. Layer 1 is simple language, just understanding the basic real-world goal, like a thermostat keeping a room warm. Then, Layer 2 layers in the technical vocabulary. This is where we start dropping in terms like microcontrollers, sensors, and actuators. Finally, Layer 3 is exam formatting, shaping those technical ideas into highly structured responses that satisfy the very strict requirements of the Cambridge mark scheme.
But wait, before we move on, I want to throw a quick question your way, just to get you thinking. Once we have all these smart devices, the sensors, the computers, the robotics, how do they actually talk to each other across a network? What are the actual mechanics of data movement that are happening invisibly all around us every single day?
Well, it comes down to 3 distinct modes of data transmission. First up is simplex. Think of this as a permanent, one-way street, like your keyboard sending data to your monitor. Data only flows from the transmitter to the receiver, never the other way. Next is half-duplex. This allows two-way communication, but crucially, only one direction at a time. It's very much like using a walkie-talkie. You have to wait your turn. Finally, we have full duplex, which is two-way, simultaneous data flow. Think of a broadband internet connection or a standard phone call. Visualizing them distinctly like this ensures you're never going to mix up transmission boundaries on exam day. All right, Paper 2, Algorithms, Programming, and Logic. We've successfully decoded the hardware and network side of things, so now we shift to the logical, problem-solving structures. Let's talk about loop flowcharts. There is a massive trap here for students, and it's mixing up precondition and postcondition loops. A precondition loop, like the while-do loop, tests the condition at the very start. Because of this, it has what we call zero execution potential, meaning if the condition is false right off the bat, the loop body might literally never run. Compare that to a postcondition loop, like the repeat until loop.
This one tests at the very end. Because that check happens at the bottom, the code inside the loop is guaranteed to run at least one time. Once you visualize where that diamond decision box is actually placed, the operational logic becomes undeniable. Moving right along to array management. Let's see how to avoid a logic trap that will definitely drain your marks, the dreaded off by one error. If a scenario gives you an array of 20 elements, let's say 20 students, you absolutely do not number them 1 to 20. Step 1, identify the total. Step 2, you must start the array counter at 0. Step 3, you end the counter at 19. That gives us student 0 through 19 to avoid any boundary data errors. And step 4, always use the specific scenario nouns provided in your prompt. Write student index rather than just some generic term. Now here's another tricky logic concept made incredibly simple. Library routines. We're going to use a pizza analogy to understand the div and mod functions because who doesn't love pizza, right? If you have 10 slices of pizza for 3 people, div, which is integer division, finds the whole slices. Each person gets exactly 3 whole slices. Mod is the remainder routine. It calculates the leftovers. After those whole slices are handed out, mod tells you there is exactly 1 slice left over in the box. So div is the quotient, mod is the remainder. Keep that pizza image in your head and you will never forget it.
Of course, we also have essential mathematical routines like round and random. Round does pretty much exactly what you'd expect. It takes a numerical value and adjusts it to whatever specified decimal places you need. So rounding 0.2456 to 2 decimal places gets you 0.25. Simple. Random generates a value within a specified range, for example, picking a number between 10 and 20. This routine is absolutely essential for creating probability and unpredictability when you're building simulators or gaming programs. Okay, it's time for a quick, tense, interactive challenge. Can you mentally apply our 4-question self-check to a brand new scenario right now? Whenever you're faced with a new system or process in the exam, you need to ask yourself, what is it? How does it work? Where is it used? And why is it better? Mentally running through these 4 pillars before you even pick up your pen to start writing is the fastest way to bulletproof your logic and make sure you don't miss a single required marking point. Because the crucial point here is turning all of this knowledge into actual, undeniable marks. Here is your mark scheme safe A-grade answer template. Step 1, clearly state the definition. Step 2, detail the mechanism of exactly how it works. Step 3, apply it directly to the scenario application you were given. And Step 4, outline the consequence or advantage. You have to aggressively stick to the rule here. 1 mark requires 1 distinct technical point. Avoid generic filler at all costs. Every single sentence you write must earn its place on the page. And finally, to execute that template perfectly, you have to master the command words. The examiner is literally telling you exactly how much depth they want. If they say state or define, be concise, get straight to the point. If they say describe, you need to step it up and provide the specific characteristics of the process. But if they say explain, you can't just list features. You must detail the how and the why of the mechanism. Matching your answer's length and depth to these specific command words is your ultimate exam strategy. Hey, make sure to subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to completely excel in your Cambridge examinations. So there you have it. That is our highly structured visual breakdown of these core topics, understood deeply, not just memorized for the short term. The tools, the networks, and the logic are now completely in your hands. So what complex computing topic should we decode next?